Now we have our template for deciding how different combinations of alternating and mean stress lead to failure for a given number of cycles to failure. And we've introduced three relations. Notice that the combinations of sigma A and M that lead to failure satisfy the equation of a line according to this template or according to this proposal. Now, the data emphatically does not lie exactly in a line, so this is just an approximation. Let's see how that approximation fits reality. So I'll just move this slide up here. Eventually we're going to make use of it shortly once again. So what I'm going to do is I'm going to try to draw the constant life curves once again. So this is sigma m, and this is sigma a, 0, 0. So there are three important parameters here. There is sigma naught, the yield strength. There is sigma u, the ultimate strength. And there is sigma f prime, which is very close to the true fracture strength. Remember, the true fracture strength is certainly larger than the ultimate strength because the true stress is always larger than the engineering stress. Okay, so now what I'm going to try to do is I'm going to try to depict the relations that I have over here. Now, those relations, the quantity in the box is just a line, and the intercept of the line is either for sigma a equals 0, it's either that point, or that point. Each choice eventually leads to a different relation, the Soderberg, modified Goodman, or the Morrow relation. On the other hand, the intercept along the y-axis is for all of them sigma AR, because that's when failure occurs with 0 mean stress. So this point is sigma AR for all of them, but the individual relations, each one being a line, differs with the choice of the intercept along the x-axis. So let's draw the first one. The first one is the Soderberg relation. And so the Soderberg relation is saying that the relation between sigma a and m, it's positive. The slope, of course, is going to be negative because we're summing both of them. As m increases, sigma a has to decrease, or m decreases, sigma a increases. So it's going to be a line that looks like this for positive mean stresses. If the mean stress is negative, then the line is going to move up like this. Okay, so certainly the positive influence of negative mean stresses, the positive in the sense that you can now apply higher stress amplitudes to achieve the same life. The positive influence of compressive stresses is reflected by this black line, which is corresponding to the Soderberg relation. Okay, well, what we can also look at is the modified Goodman relation, which has to do with this intercept. Again, the other one is the same, so it's going to be a line that moves up like this. Okay, and if we insist on going into the negative sigma m values, again, sigma a value, corresponding sigma a value is larger to achieve the same life. Again, the positive influence of compressive stresses reflected. And finally, we can also look at the Morrow relation, which is the most useful among these for us, at least presently. And so it's going to be a line with that intercept. And the red line, if we insist on moving to the negative mean stresses, again, has similar qualitative features. So that is the Morrow at the very top. Soderberg is at the bottom, and in between you have the modified Goodman relation. So those are the three lines. Now, you might wonder at this stage where the data is. Now, the data points, it turns out, they are located, just qualitatively plotting at least a few, they are located like this. So in other words, it's not first of all a straight line. I already know that it's not a straight line. Look, it's not a straight line, right? The constant life curve is not in general a straight line. And so I don't expect to see such a straight line. But on the other hand, I see that somehow there is a line that seems to go towards sigma u. Now, what one can do is one can try to sort of fit something that is representative of what is going on there as well. So, and such a line would perhaps, for instance, a simple curve at least would be the following one. Okay, now I've drawn that in a certain special manner. Now you see it goes up like this, and then it takes a zero slope there, and then if you were to continue the line, the natural way to continue that would be along that direction. Okay, so it's sort of like a parabola, and that's in fact called the Gerber relation. So the black points are the data, and then we have three lines associated with Morrow, Goodman, Soderbergh, all having to do with this simple template that we have as a relation, right? That template. And we also have Gerber. Now, what Gerber is really doing is he's saying, well, okay, if this is equal to 1, I get failure, and that's equal to 1, I get failure, but I don't agree on summing them. Instead, what we're going to do is we are going to take the second one and add it with the intercept being sigma u, add it after squaring it. Because if I do that, I can get a curved line that is more reminiscent of the data. It doesn't still fit the data, notice, but at least it is curved and not straight. So, and the other part remains the same as in our old template. So that's equal to 1 is another relation called the Gerber relation. Now, I'm just mentioning this, and we don't quite want to use the Gerber relation very frequently for the following reason. Now, first of all, it does, of course, seems to replicate the data's nature a little bit better, but it has two shortcomings. One, first of all, it incorrectly predicts the influence of the compressive stresses. When I apply compressive mean stress, then I expect to be able to apply larger alternating stresses compared to the completely reverse value, a larger stress amplitude compared to the completely reverse value to achieve the same life. But here it's saying that that value is actually should be decreasing, which is not correct, doesn't make sense. So it is incorrectly predicting the compression effect. Compression effect is positive, but it is predicting a negative effect, okay, as if it were positive. And that's because we're taking the square and not looking at the sign of sigma m. Now, second is the following. It is non-conservative. And what does, again, conservative and non-conservative mean? Well, remember, there's always the concept of a safety factor. I'm going to increase sigma a and sigma m, let's say, proportionally from 0, and I'm looking at when failure occurs. So as I move along, the model that predicts failure first is the most conservative one. So as I move in a certain direction, black predicts failure first, because that's the line, that's the combination of sigma a and m that lead to a certain life. So that's the Soderbergh. Modified Goodman predicts that I can apply a larger combination of sigma a and sigma m to reach the same life. And Morrow, even larger. The data, even larger, but Gerber, the largest. So Gerber is the least conservative, in fact. Now, with respect to data, with that point of view, we see that all of the lines here are actually conservative. So the lines are conservative. So it is actually perhaps not a bad idea actually to use one of these lines. And what we've said is that among them, the red line, the Morrow equation, with the critical value being equal to the coefficient that appears in the Basque-Cohen equation, that is one that we like to use at least for steels. That is the view that we have, and that view, the Gerber relation, okay, so we just mentioned it, but still that is a possibility. In the future, perhaps people come up with better relations, but the one that we like is actually the seed of the discussion for Gerber as well. This is the one that we like, with the critical value, in particular having the value of the constant that appears in the Basquin relation. Okay, so now based on that, we're gonna proceed ahead and see how exactly these equations, these constant life curve models, are going to help us solve problems of interest.